So we're going to look at Unit 6, Lesson 2 here in the Introduction to Exponential Functions. So hopefully yesterday you wrote down the two vocab words that I had in the announcements. If not, you need to do that first and then go ahead and start this example 1. So we're going to start with just the key features of what the parent of the exponential function would look like. So the equation that you should have written yesterday is f of x equals a times b to the power of x is the form that we're going to use for exponential functions here. And yesterday in your notes, I stated that b here is your constant ratio. So we look at this first equation, or as I call it, the parent, the most simple form of exponential growth here, is you notice that your b is 2, and you'll notice it has an exponent of x, but the a is mathematically there, but it's not visually being shown. So, of course, if you want to rewrite that with an a in it, you would have to put 1 would be the only other value that would mathematically work without changing the whole entire problem. So if you want to think of it as 1 times 2 to the power of x, the a is 1 and the 2 is your constant ratio of 2. And of course, the constant ratio, like you were supposed to write down yesterday, is the repeated number that you repeat over and over, which we know if we multiply the same number over and over, that's the exponential idea. So when we go ahead and start using or going ahead and making this table here so we can graph, so we can look at these key features of an exponential function. We're going to output table here. So we're going to input -3. So 2 to the negative third power, and I want to leave everything as fractions. So that'd be the same as saying 1 over 2 to the third power, which is 1/8. And then 2 to the negative second power would be 1/4. And we kind of talked about this pattern a week ago, with that every time you go down on this one, since the base is 2, you're going to divide by 2. And in this case, we're going to multiply by 2 because we're going up in value. 2 to the negative first power is 2, 1/2. And then 2 to the 0 power is 1. Anything to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. And 2 to the third power is 8. So we're going to go ahead and try to graph that. And I apologize, my stylus isn't working, so I have to do everything with just my finger here. So we'll see if I can graph halfway. Make that a little bigger. So we have -2 1/8, -2 1/4, -1/2, 0 1, and then 1 all the way up to 2, and then 2 4, and then 3 8. Let's see if I can try to draw a curved line there. Not the best, but you can kind of get the point. So let's go through some of those key characteristics that you kind of notice when you first look at an exponential function. I'll type these so we can see them just a little bit better. So the first thing I notice is that the y-intercept is 1. So 0, 1, because it's an ordered pair. I notice the graph is increasing. If you want to talk mathematically, every time we go up in this table, the graph is doubling in size, so you can write doubling. I would say that the constant, we kind of already talked about this, but I'll write it. The constant ratio, which you remember is b, is 2. And then I also talked about that the a in the equation has a value of 1. And so you're going to start seeing some patterns here. You could talk about that the domain. So in other words, all the values that I could put in for x right here, there's all real numbers. The range, so let's talk about the range for a second. So even if I go backwards, and we kind of had this conversation about having negative exponents, even if I continue to divide by 2, 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 will this line ever cross the x-axis? And the answer, of course, is no. Okay, so even if I divide by 2, divide by 2, it's going to get really, really close to the idea of 0, but it's the y being 0, but it will never be past 0. So my range is all real numbers greater than 0, because that line would never. And while we're talking about that, one of the vocab words that I had typed in there for you is called an asymptote. And the asymptote, if you look above you there, is a line of a function that gets closer and closer and closer to, but never intersects. And in this case, that equation here is going to get really, 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 really close to 0, but never intersect, and it's a line. So my asymptote would be y equals 0, because that's how you would label the x-axis. So I want you to think about if I was doing a half, and if you need to jump on Desmos, you can, and go ahead and put in the function f of x equals 1/2 to the x power. Pause this video, look at it, come up with some key characteristics, and then push play and see which different ones that you have that I am going to talk about right now. So if you look at this graph, and again, put it in Desmos if you need to visually see it, you're going to notice that the y-intercept is, again, 0, 1. You are going to notice that the graph this time is decreasing. So opposite of what we just looked at in our last one. Okay, and this time if you want to say that they're like decreasing by halves, so instead of doubling, multiplying by 2, this time we're going to have the idea of multiplying by a half or dividing by 2. You can say that the constant ratio, or the letter B, sorry, is 1/2. You can say that the value of A is 1 again, because there is an invisible 1 right there, would be your A. You are going to notice that the domain again is all real numbers. So I can plug any number I want in for the x and get some type of output. Speaking of outputs, the range is all real numbers greater than 0 again. So this graph is going like this. As you look in Desmos, it's going to go down and down and down and get closer to 0, but never cross the 0. And since we're talking about the line that it never crosses, we're going to go with the idea of asymptote here, if it let me type asymptote. And so my line of the asymptote is going to be y equals 0 again, because again, that line is going to get really close to 0, but never cross. So the asymptote, spelling that wrong. Asymptote is, I'll fix it here in a second, y equals 0. ASYM PT. I'm missing that T in there. T. There you go. Okay, so that's just a couple examples of this first one was a increasing and kind of how those characteristics of that parent function of an increasing, and then this one should be a decrease. And again, I hope you looked at Desmos so you can kind of see those key features of what an exponential function is going to look like. So example number 2, we're going to get into looking at a storyline here. So it says a network administrator, uses the function f of x equals 5 to the x power to model the number of computers a virus spreads to after X hours. If there are 1,000 computers on the network, about how many hours will it take for the virus to spread to the entire network? So think about our independent dependent variable here. So independent, what's varying here is going to be our hours are going to be changing. Let's see if I move that over a little bit here. So we have hours is our independent, and then our dependent. So as hours are increasing, the number of computers being affected is going to be our output. So if we use our input-output table here, if I input 0, so 5 to the 0 power, hopefully you understand that's 1. Ooh, sorry, again, writing with a finger instead of a stylus. If I put 5 to the first power, that's going to be 5. 5 to the second power is going to be 25. 5 to the third power is 125. And hopefully you're seeing that repeative. Remember, B is 5 here, and that repeative number, that constant ratio, as we're keep multiplying by 5. 5 to the fourth power is 625. And then 5 to the fifth power is 3,125. So we're going to go ahead and graph that and label it here. So we're going to graph number of hours, I said, was our independent. And our dependent is number of computers. And let's put some points on this graph. So at 0 hours, I had 1 computer affected. And these are going to be really tiny numbers here because notice that my axes are going up by 50. At 1 hour, I only had 5, so you're going to barely see that. See a little dot there. At 2, we only had 25. It's about right there. See if I can make a line. Maybe that'll be easier to see. At 3, we have 125. So 50, 100, 125. So somewhere right there. At 4, we have 625. So notice how fast we're growing. About right there. And then 5, we have already over 3,000, which I can't even graph. So it's going to be up here somewhere. So I'll try to make as there curved line as I can here. So it's going to start here pretty slowly infecting our computers, and then it's going to take off pretty quickly after 5 hours. So the question is, oops, sorry. If there are 1,000 computers in the network, about how many hours will it take for the virus to spread to the network? So if we go to 1,000, which is this line right here, so I'll graph, make a quick line here, graph where y equals 1,000, and I'll label that y equals, oh, I'm still in the 1,000. Okay, because that's what this is. Approximately, it said how many hours. So I can kind of look down here, and I know my graph isn't perfect by hand here, but I can definitely tell it's going to be past 4 hours, not quite 5. So I would say a little over 4, and it looks like 1, 2, 3, 4. So going up by twos or point twos, 2/10. So somewhere around 4.2 hours. So if I want to check to see how close I am, if I put in my calculator here 5 to the 4.2 power, and I'm just kind of guessing by looking at my graph. And again, it's not a perfect curve I got going on there. Give me a second, put my calculator here. 4.2 hours. I only have 862.3 and then continues there. So I'm going to try one more time here. Let's go 5 to the power of 4.3. And now I'm over 1,000. So I got 1,112.9. And so on computers, so my better estimate here, after looking at my graph and then using my calculator to do a better estimate, that my better estimate is going to be this 4.3 hours, 1,000 computers. So if you just think about exponential growth, that's crazy. We started with one computer at 0 hours and already at 4.3 hours, so a little over 4 hours, I'm already infected 1,000 computers, and my constant rate was 5. Okay, how long will it take to get 5,000? Okay, this is just going to be a little guess and check. It's kind of hard to see. Let's just start with, so grab your calculators. Let's go 5 to the, let's go 6. So in 6 hours, we'll see where we're at here. So that's 15,000. We're not even really close here, but I'm going to guess 5 to the 7th is going to be too big. That's already 78,000. So let's try 5 to the 5.5. So 5.5 hours. Again, we're only now at, oh, I didn't mean 5.5. Let's try 6.5. Try that again, because I know it's over 6 hours. That's 34, almost 35,000. So let's try 5 to the power of, and I guess you can't see me doing this with my calculator, but I'm just using my calculator. Let's try 6.7. It's 6.7, I'm pretty close. So 5 to 6.7 hours, I have 48,206 if I round. So if I go one more, we're just going to go by tenths. I know I can get really detailed and go by hundreds and thousands, but we're just going to use an estimate idea. So if I go to the 8th, now I'm over. So it's going to have to be, you know, if you're just going to the 10th, about 6.8 hours, and that would be 56,623 computers. So my best estimate of how long it would take just to the 10th, and if you want to get to the 100th and 1,000th, you are more than welcome to try a little more, but it's going to take at least or a little bit before 6.8 hours to spread to 50,000. So a little in 6 hours, not very long. It's going to be almost over 50,000. Okay, example number 3, we're just going to go ahead and just look at the table and come up with the equation that would represent this table. So if you didn't notice when we were doing the key features, and maybe some of you notice, and I'll just put the equation format here, that of course the b is my constant. What am I multiplying by each time? My a is my y-intercept. Okay, so on both of the examples that we graphed, our y-intercept was 1, and so was our a. So a is the y-intercept. So when looking at this table, I can see it starts at 4. So that's definitely my y-intercept, because where x is 0. So right here is my y-intercept. So I know this is 4. I'll put my y equals. And remember, b is the constant ratio. What's it multiplying by? Well, 4 times 3 is 12, times 3 is 36, times 3 is 108, times 3 is 324. So this equation would be y equals 4 times 3 to the x power. Okay, let's look at b. Let's look at it in a graph, or yeah, in a graph. So again, this is your format for exponential, y-intercept, and then the constant ratio in which you're multiplying by. So the first thing I notice right here is that my y-intercept is 0, 128. So y equals 128 times, now what am I multiplying by? So if you want to, you can think of it as a division idea, but then when you write it as a constant b, it's what you're multiplying by. So if I look at some of these, 64 divided by 2, you're dividing by 2 here, is 32 divided by 2. Oh, I missed 3. Oh, there it is. I was going to say, it can't be 8. Is 16 divided by 2 is 8 divided by 2 is 4. So if you put 2 here, though, that's what you're multiplying by. So this would be a growth. It'd be going up. But since it's going down, yes, you're dividing, but the opposite or the inverse of dividing by 2 is multiplying by a half. So that would be your equation. Okay, go ahead if you want to pause the video, you can, and try these two on your own and then see if you get the same thing I do. So looking at this, I'm going to get f of x equals, my y-intercept is right there for me. So that's my a times, now I'm going to look at my y values because that's what you're multiplying. So 3 times 4 is 12, times 4 is 48, and so forth. So my equation would be 3 times 4 to the power of x. Then I have, this is a big y-intercept here, 2,187. So f of x equals 2,187 times, ooh, I'm going down, so I know it's going to be fractional. And if you struggle with trying to figure it out, you take your calculator and divide backwards. But this is going down by 1/3. Yes, because 27 times 3 is 81 times 3 is 243. So this would be dividing by 3. And the inverse of that, because remember, it has to be multiplication, is 1/3 to the x power. And the last example today is just comparing the difference between linear and exponential. So it says Tasha is offered 2 pledge options for donating to charity. Which option will increase the pledge faster over time? So option A here, we get $100 for the first week. There's going to be week 0, the beginning. And then each week after that, the amount increases by 25. So hopefully when you're thinking about this and you're writing it down here, that you know that this is a linear function because you're increasing by adding the same amount each time. And the example B here, we're going to start with $1. So big difference, $100 to $1. And then it says we're going to triple every week. So $1, triple that is 3, triple 3 is 9, triple 9 is 27, triple 27 is 81, triple 81 is 243. So notice that after just 5 weeks, you have more money than the linear. This is exponential here. Exponential. And you're going to already know that the exponential is going to grow at a fast rate because this one you're multiplying by 3, and this one you're just adding 25. And of course, the idea of multiplying by a number greater than 1 is going to be faster than adding a constant rate over and over and over. So the answer is exponential. This is going to grow faster because you're multiplying instead of adding the same number each time. So to try it, you can stop and then look at what we wrote down, or you can just listen as I talk about them here. So it just says identify and then explain if the function is linear or exponential. So f of x equals the number of branches at x level in a tree diagram where each level of branch exceeds into 4 branches. So one branch goes into 4 branches. Those 4 branches go into 4 more branches. And this is definitely an exponential idea. Ooh, that's some beautiful branches going on there. An exponential idea because you're multiplying by 4 each time. So this is exponential because you are multiplying. Sorry, I'm just going to shorthand this because it's pretty hard to write with my finger here. By 4. Or you can say something about the constant ratio A is 4. Our other function we talked about here is equals the number of boxes in a row X on a stack in which each row is increased by 2 boxes. So you have a box, and then each row you add 2 more boxes. So as you heard me say, add. So this is definitely linear because you're adding 2 each time. So hopefully this helped. Your expectation is to get your Math Excel done by Monday, and have a great weekend.